Welcome, everyone, to this Machine Learning in Medicine seminar series. My name is Shyam Visveshwaran, and I'm co-hosting this with Kian Bratmanigalich from Pitt, as well as with Jeremy Weiss from CMU. So this seminar series is focusing on new algorithms, real-world deployment, and future trends in machine learning in medicine. And we are featuring investigators who are developing and applying machine learning to biomedical discovery and clinical decision support. And as most of you know, this runs every other Wednesday at 3 to 4 p.m. And with that, I'm going to hand this over to Kehan to introduce our speaker for today.
Thank you very much, Shyam. It's my great pleasure to introduce Dr. Romi Chunara. Dr. Chunara is Associate Professor at NYU, jointly appointed at the Tandem School of Engineering in Computer Science and a School of Global Public Health in Biostatistics and Epidemiology. Her PhD is from Harvard MIT Division of Health Science and Technology, and her bachelor degree is from Caltech. Her research group focuses on developing computational and statistical approaches for acquiring, integrating, and using data to improve population-level public health. She is an MIT TR35 and NSF Career, Facebook Research, and Max Planck Sabbatical awardees. Thank you very much for accepting our invitation, Rumi. We are excited to listen to your talk.
Great. Thank you very much, Kehan, for that introduction and for the team for the invitation. I'm going to see. How does that look?
Perfect.
Okay, wonderful. All right, so I'll just dive right in, and then as I proceed, I'll just tell you about how the talk is organized and when might be good to ask questions. So today I wanted to talk about some ongoing threads of work in my group that look at this idea of generalizability and robustness in machine learning models, and how, especially when we're applying machine learning to any human or societal level systems, these questions of equity are going to be inherent, and especially when we're thinking about transferring models to new environments and how they'll perform in new test data. Okay, so thinking about our standard definitions of generalizability and robustness when we talk about machine learning. So generalization, we're typically referring to a model's ability to adapt properly to some new or previously unseen data. So usually drawn from the same distribution as the one used to create the model. Robustness is the property that characterizes how effective the algorithm is while being tested on some new independent, but also similar data set. So I just made this little abstract visualization here to show that now when we're talking about data sourced from humans, like people or about people, then we're naturally going to have to think about concepts of equity as well, especially when we're thinking about a new distribution, right? So that new test set, whether that's in a new, maybe a new hospital, maybe a new location. And so these are the common issues that will come up. This is further made imperative by some of our recent, the recent findings in the literature, and these are from the media as well, showing that medical machine learning AI systems are disproportionately built with data from just 3 states. So I know probably Pittsburgh, there's a lot of work happening as well. But just by the density and by the population, you can guess these are coming from New York, Massachusetts, and California. And so if we're thinking about model usability, maybe in a new rural place or somewhere where there's not primary development going on, we're going to have to think about how models developed in these limited places are going to be used in such a new environment. And of course, what we've seen is that we have issues related to bias or equity or fairness in all sorts of systems, whether that's having to do with image data, text data, or in some cases, like even healthcare specific data, claims data in this case. And so these issues have commonly come up. The final motivation slide is that this is especially imperative because already, because of issues kind of intertwined with these same ones we're seeing, but also pre-existing, is that inequity, in this case in mortality, and this is data from the National Academies of Science, so from the US, has been actually, these inequities are widening already. So from 1980 to 2010, we see, and this is mortality percentages for groups of women at different socioeconomic levels, that the poorest women's mortality or life expectancy is actually going down, while for the richest it's going up. So this inequities are already widening. So we're kind of working on top of these disparities. Okay, so today I'm going to, in reference to this general topic of generalizability, robustness, and equity, go through 3 different papers that are pretty recent. And so I think there's some natural breakpoints in between these, each of these. And so I'll pause there and can take questions then and as well at the end. All right. So this first work was actually really motivated by a couple of things. One is that there are just increasing sources of health data, right? So if we're trying to understand, and in this case, this work was also motivated by respiratory infections. This was done prior to COVID. But if we're thinking about sources of information for early detection of infectious diseases, or even understanding what symptoms are predictive of the disease, this information could come from a variety of sources. Could come from the electronic health record, of course, but we also have a lot of other informal data sources that are used, including by the CDC, to get that earlier sense of when either a period, like a seasonal or a surprising epidemic could occur. And so that could be from social media, or there's a lot of cohort-based online reporting systems in different countries. I've put some of the logos here where, and folks might have seen more of these come up during COVID, where folks online kind of sign up and will report their symptoms on a reoccurring basis. And then in some cases, actually also send in a specimen, like a saliva or nasal swab specimen, so that it can be matched up with the symptoms that they had. Here is the data that we used in this study, but I wanted to show it up front to show how from different data collection mechanisms, or in this case, different studies, the actual population represented could be quite different. Okay, and so here we're looking at 4 different data sets. One, the yellow goldish one, is from a study that we did the primary data collection for in the New York and Northeast area, where folks reported online what symptoms they had weekly during respiratory infection season, and then also sent in specimens if they had any respiratory-like symptoms. And so we were able to do PCR on those and confirm what the infection type was. The Flu Watch is a similar type of study where folks reported online in the UK and sent in specimens. The Hong Kong study is a more household-based study where, in this case, some community health workers were sent to the home of people who had an infection to then sample from their social network contacts and see if there was any secondary infections. And then finally, the Hutterite study was also, in this case, a nurse went out to a specific community in Alberta, Canada, and was again sampling people to look for, look at influenza prevalence. And so these 4 studies, all done for surveillance and epidemiological purposes, have different population distributions in terms of age and also gender. Okay, so before I get into the details of what task we're looking at, I just want to introduce the fact that we're going to use directed acyclic graphs in actually all of the studies. So this is a good point to introduce it. Now, a little bit background for those who just maybe haven't done that before. The graph will contain nodes as well as interactions between the nodes, the arrows between these nodes where the letters are. And there's various requirements for the DAG in that each arrow should only have one arrowhead, each arrow points to only one variable, arrows don't point to other arrows, and they don't split or merge. And so we'll require them to be acyclic, no closed loops, and no variable can affect itself. Now, the reason that we are using them in these studies is that this kind of approach can make our assumptions clear about which variables interact, how they affect each other's, and we provide explicit rationale. Where does that rationale come from? Either in this case, domain knowledge, you'll see in many of these studies, where especially from the health side, we'll have some domain knowledge about how health-related factors, biomarkers, et cetera, will interact. But of course, there are limitations as well to this. So it's good because it makes our assumptions clear. It's leveraging domain knowledge, but there could be unmeasured confounders. That's a possible limitation. It also makes our computations straightforward once we have a DAG, because we know that the joint distribution, the joint probability distribution overall of all the nodes is given by the product of the conditional distributions of each node given its parents. So that way we can compute outcome probabilities in a straightforward way. Okay, so zooming back to our task here, this is actually a nice task because it's very simple. This influenza prediction one, it's somewhat in the milieu because of all the COVID, we're during the COVID pandemic. But it's a very simple task, and the graph then itself is straightforward, and it's a good way, it's a good exemplar for the algorithm that we're proposing. So in this case, for the graph, we'll rely on what we know as the data generating process. So we'll have our outcome, which is influenza status represented by Y. We'll also have data on what symptoms the person reported, and so that'll be a vector of binary values, like for cough, runny nose, etc. And then we also will have the demographics for every individual, so what their age and gender is. Now, we know that what your influenza status is will affect if you exhibit symptoms or not. So that's why we have an arrow pointing from Y to X. And then we also know from the epidemiological literature that the demographics can also affect what symptoms are exhibited. For example, younger people might exhibit different, tend to have different symptom profiles than older people, okay? And that could also, demographics can also affect your influenza risk. So that's why we have arrows from D to both X and Y. Okay, so we're gonna clarify the task even now via the slide. So again, for what we're going to have is, reading on the bottom here, we want to predict the influenza status for individuals in each of the subgroups based on data from some training domain and limited outcome data from a test domain. So what are the domains in this case? It's going to be these different data sets. So for example, I could have data from the Hong Kong study about, for each domain D, I'll have the vector of symptoms that are exhibited, what the corresponding infection status was, the age and gender of the individuals, okay, for all individuals I in that data set. Now, again, I could have data from the Hong Kong data set, and I want to see if I can maybe predict in my New York study what the infection probability is, given I know just the symptoms and the age and gender of people. So maybe I didn't get to actually retrieve samples from the people in New York because of course that's more resource intensive, it requires cost and time, but I want to leverage the data from these other studies to see if I can predict well in a new one. So in our case, we're going to require limited outcome data from the test domain. So meaning that I might have a few validated values of Y for my New York data, but I don't have it for the entire data set. And in particular, we want to also make sure we can predict well for each of the subgroups. So we're going to look at that prediction by age and gender as well. Now, another reason we are leveraging this idea of the causal graph is because we can also input where the sources of instability are. In this case, both across domains and as well within. So we have two different sources of instability here, okay, and we're denoting them via these selection nodes. That's the square nodes here with the S's next to them. And there's two different sources. One is we know that the symptoms that could be exhibited in our different settings, in this case, the Hong Kong study versus the Hutterite one or the New York one, could be different just based on the strain of influenza maybe that was circulating at that time point that study occurred, or just based on other contextual factors. So that's why the variance by domain points to X. So that arrow goes down to the X. And as well, we can also have another selection node from D, because we know that we're going to have demographic differences across the domains. So that's also going to be differences across domains, the differences in the distribution of individuals by gender and age. Now, then using this these presence of selection nodes, we can actually see where the independences are in our graph. So in this case, we're looking at the probability of the outcome Y given the symptoms, and that's going to be different across the environments, right? Because of where we put the selection node. But we also know that the shift is independent of the outcome given the demographics. So you can see, yeah, that's why S is not independent of Y given X, right? So that means that we do need some local information. We do need some X information along with Y from our new test domain. But on the other hand, because S is independent of Y given D, we can leverage this probability of Y given D across the environments. Okay, so that's kind of articulated just in terms of independences in the graphs, but actually this corresponds to epidemiological knowledge as well, which means that the likelihood of infection for older people versus younger people, that's going to be consistently increased no matter what study you're looking at or where these places are. All right, so yeah, so if you're more familiar with the language of causal graphs, you can also interpret this as X doesn't deseparate S and Y, right? S is not independent of Y given X, but S is independent, as I said, of Y given D. Okay. Okay, so leveraging these two facts, we then can create our graphical model for our prediction task. And what we'll do is we'll leverage the fact that we can actually use the demographic, the marginal probability of Y given D. We can leverage PY given D across environments. So we can leverage our probability of Y given age and gender across the environments, but we do need some domain-specific information from each of the environments. So using those two facts, you'll see how we set up our Bayesian learning problem. Now, hierarchical Bayesian models have been typically used in fields like natural language processing, where, for example, in those settings where you want to predict maybe the next word in a sentence, folks have actually used the source of the text data as an invariant parameter in the learning process. So, for example, if you have the word monitor in a natural language processing example, you know that could inherently have some different meaning if it comes from maybe a computer manual versus like a website. And so in that case, this is where people have kind of used the idea of some invariant aspect to the learning based on the source of the information. Now, in our case, we know what's going to be invariant is the actual contribution based on the demographics. And so what we have here, and I'll start from the bottom, is we have a plate for each of the different domains, right? And in each domain, we have that vector D, right? Which consists of the symptoms and the corresponding outcome information. In this case, the presence of a flu or no flu, and then the age and genders linked to those. We have the associated parameters, theta, and we have some prior information, alpha. We have the priors, which will show what we just assumed the values to be. So above each of the plates, then we have a parameter specific to that domain, similar to the NLP example I gave, where we look at where the data is coming from. And so in this case, we've divided it into two separate types of data sources. The CS stands for crowdsourced. So it's our data sources where people are reporting data themselves online. And then the HW stands for health workers. So it's the data sets where we have a health worker going to someone's house and recording down the symptoms themselves. We separate those because previous work by our group actually looked at data, the prediction of outcomes from different data sets. And as you can imagine, the crowdsourced data sets are much noisier. And so we can separate those out this way. So then above that parameter for the data source, we have the parameters for, again, age and gender. And then at the top, we have a population invariant parameter. So then this, so then let me see, yeah. So just a recap is that our task is to predict Y, the infection in our target environment with little training data. And basically what we're doing is using invariant information, the probability of Y given the demographics from the other data sets to actually help the prediction in the new domain. And so the objective function looks like this. I'll just go over it briefly for you. So we have for each data set L, we have, we're summing over each data set L. J is any overall value for each symptom. So each symptom overall across all the data and all the data sets we have. F sub j is a statistical measure of the symptom J, and in this case, you can think of it. We actually use the positive predictive value. So what's a PPV for that particular symptom overall, and then we have some regularization with lambda. So yeah, here we have then the parameter for that symptom in the data set. And then here we have, and then K here represents the parameters for the symptom in each data set. So we're kind of looking at the predictability of symptoms overall, and then accounting for how predictable the symptoms are in a specific data set. Finally, outside here, we have this term, which allows us to set how much divergence we want between the child and parent nodes in this whole model. And so, yeah, so this allows us to control how much those are kind of brought together. So yeah, based on hyperparameter tuning, we figured out a value for beta, and I think we used a simple L2 divergence in this work. All right, so before I get to showing you the results of that prediction of Y given small amounts of data in our new domain, we also in the paper talk about provide the conditions under which this invariant learning fails. You can imagine that in certain scenarios, like for example, you might not have enough data from the new data set, or you might have a population distribution that's it's skewed too much differently from the other data sets you have, and you can't leverage any of that invariant information. So we provide those conditions there. All right, so to look at the results, so before I dive in deeply to the graphs, I just want to give overall that yes, this method, I'm calling it the hierarchical population method, higher plus pop, because we leverage the invariant components, and we also leverage the population specific components. This performed better than several baselines, given when we looked from 5% to 25% of the new data. So again, we had some data in the new domain, but it's a very small amount, 5 to 25%. We compared this against several other approaches. One is the pink, the next line below green, that in terms of performance is leveraging the invariant components, but not pulling out the population specific variables separately. So we didn't leverage the age and gender and the fact that those will affect the probability of an infection. So that one performed slightly worse. As well, I'll just point out broadly together, FIDA is the frustratingly easy domain adaptation. Folks might have It's a common baseline. Basically, it just concatenates all the features in one space. So you're not doing any you're not leveraging the hierarchy at all. And we looked at that with population parameters and without. And then we looked at a simple logistic regression, and we also looked at the setting where you only have your training data and you don't know anything about the test. And so that worked the best when we didn't have any target data. It worked higher when we didn't have any target data, but then that decreased performance once we started inputting new training data. The other methods would outperform that. So that's just a broadly assessment of how the different methods compared, and you can see that both leveraging the invariant parts and the population parts improve the model. And there's two graphs here because I'm showing this when we're testing on two different data sets as the outcomes. We just systematically did this by leaving out each one of the different data sets, and the results were consistently positive for our algorithm. All right, so I'm going to pause there and just see if there's any questions.
If there's any question, please raise your hand, or alternatively, we can ask the questions at the end.
Okay, yeah, so let's see, I don't see any. I'll keep talking. So yeah, so this study showed us how leveraging these differences in the population actually helped us in terms of prediction for this task. Okay, Michael, you have a question?
Mike, you have a question?
I was muted, sorry, and I was slow to raise my hand. So I'm having two-factor problems here. So you talk about generalizability and dealing with bias, and rigor, reproducibility are the big parts of this. And I know this is a basic question, I probably should have asked it earlier, but how do rigor and reproducibility map into these algorithms for generalizability? Because we're getting progressively held to higher standard for much of the work we do and the data sets we share to hit those higher standards. So where does this all map together?
Yeah, that's a great question, Mike. Okay, so let me break it down a little bit, right? So basically so once we are having more axes on which we want to perform, then of course, yeah, it's going to be that's going to be a more difficult task, and as well the reproducibility of that might be difficult given you're kind of fitting more and more to what your specific data set or task looks like. I guess I would say a few things. I think this example also really exemplifies how, the domain, like the topic of the task and the domain knowledge, I think was essential here. So as you can see, the whole task the way we set up the model, it all hinged on what the graph looked like. And that was based on our knowledge of the system. And so, when we're talking about this, the generalizability of this algorithm across these data sets, we show that works well under specified conditions. If you're going to go to even a different task, maybe a different prediction task, right? Maybe a different infectious disease, we might have to reconfigure our original graph. And so the following steps would also change, again, according to that graph, what's independent and what's not. So I would say that those challenges will come up, but I think we need to perhaps look beyond simply looking at the data to try and guide us, but instead maybe looking at some of the task knowledge as well. Because thinking of this more as the pull pipeline, that was an important part of it as well, besides just the algorithmic formulation. So that's just one comment I'd give to your question based on this specific project. But I think that's broadly important as well. Besides just looking at a generative approach, leveraging some of that prior domain information will help us stay more attuned to the task. But of course, that's going to make our job a lot more difficult when we try and switch tasks or switch, to something with a slightly different model.
Thank you.
All right, so yeah, that was a great question, Mike. I think it really helped me discuss just what this paper exemplified. It's kind of this whole pipeline. The task was fairly simple task, the simple graph, but just the idea of leveraging what knowledge we have on this, in this case, the epidemiological side, to then shape even how the model is designed. Okay. The next one we'll look at, again, is going to leverage a causal graph. So you'll get to see that. And in this case, the task we're looking at is slightly different, which is to guarantee fairness, algorithmic fairness, which I'll define, folks are likely familiar, and robustness across domains where you don't have, in this case, any information about the test domains. So slightly different scenario. Okay, bringing it back to the original motivation I also showed, this is really pertinent because, again, a lot of models are being built in specific contexts. How do we even know how they're going to perform in a different setting, where the distribution of data is going to look different? And I'll show a little bit of data at the end on that in some ongoing work that we're doing. All right, so I'll just motivate the problem through a stylized example. So say we're a healthcare provider that has multiple hospitals across the country, and we want an algorithm to decide how to allocate some limited care resources in an efficient and equitable manner. So for example, we want to decide which patients to follow up more regularly with. And so with these goals of doing this in an equitable and efficient manner, we might take data from one of our urban hospitals, or it might be a center where they've been developing a model and want to do that such that we can use it in our new hospital. Okay. So yeah, so here a little bit filling in more of the icons of what's happening. We've developed our model in this one hospital. We want to develop it such that it would be fair before we've seen anything about the deployment environment. And then, that could be a rural hospital. Maybe it has a slightly older population, different healthcare practices. So you can imagine the data distributions are going to be different, but we want to ensure that what we've designed will still work and be fair. So in sum, our goal is to build a model which remains fair and accurate as the data distribution changes. So some work, of course, started looking at this these types of scenarios, but typically for an accuracy goal, right? So in domain adaptation, you have different kinds of work. And some work also has looked at both fairness and accuracy as goals, but this typically would require some deployment data, right? So just like in the previous work, we required some information from our test domain. That's also one scenario that people have looked at. And also, it's also worth mentioning these other previous works have not characterized when it is possible or impossible to build a model that remains fair under shifts, right? So to do that even in advance of deployment. Okay. So yeah, so in this case, in contrast, we're going to look at unfairness as well, unseen shifts, and we'll provide the conditions for when this will work. Okay, so in this setup, this fair learning problem, we're going to use a typical empirical risk minimization framework, right? So we want to minimize some loss subject to some loss given some parameters and data distribution P. And we want to also do that subject to these fairness constraints, okay? And so we have some fairness constraint that's going to be less than epsilon, and I'll define what that is. So the loss, for example, could be the squared error between the true and predicted outcomes averaged over the observed data distribution. And then the fairness constraint, it could be a variety of things. We could use some of the algorithmic fairness metrics that folks might be familiar with, for example, demographic parity. So in this case, you aim to control the difference in your predicted outcome, so y hat with the parameters theta, given these different sensitive groups. So you want the difference between probability of y hat given your sensitive group alpha is a 1 versus a 0 to be less than some epsilon. Now that, let me visualize what that means for folks who might not have seen that before. So in this case, in demographic parity, you can maybe think of the situation where you have some task and you want to predict your outcome, but you want to make sure that you've predicted it equally for maybe folks who have red hair or versus not red hair, right? So in this case, the sensitive property is this hair color, and then A is equal to 1 might be the folks with red hair, and A equals 0 is folks without red hair. And you want to make sure that difference is the difference of the predicted probability is less than some epsilon, some threshold. Okay, so the naive approach would just to be ignore any possible distribution shifts between your training and deployment environments and just learn what you can from the training distribution and then use that in your deployment. However, these could, the constraints of loss and fairness could change arbitrarily depending on these distribution shifts. So you could learn some correlations that might exist only in the training data, and then it would incur high loss in the deployment data, right? So there won't be any way to guarantee performance. So the key idea for us is to ensure that both the loss and fairness constraints are going to be invariant under whatever possible shifts you can have. Okay, so that means we're going to restrict to the parameters for which the following is true, where the loss and the fairness constraints are approximately the same across the environments. Now, this also maybe relates to Mike's question, is that by restricting the class of models, you can lose out on accuracy because you're going to ignore some valuable information from the training data. But your trade-off is that by ensuring this invariance, you're guaranteeing good performance for unseen test distributions. So you can think of this as a different task. If you wanted to build a whole new model if you wanted to achieve just maximum performance in your new environment, then that's a whole different task. And you can imagine you would go about it in a much different way. Okay, so I'll represent our solution now in terms of the graphical model here. So first, we'll have the DAG, this is the abstract one. In this case, a causal graph. We can again generate it via some domain knowledge of our specific medical task. And we can represent where the shifts can occur, okay? So first step is to represent all possible shifts in this causal graph. And then the second step would be to identify which information is invariant by looking at interventions on the graph. So basically you want to cut out where the shifts can occur, and then you're left with the invariant relationships, and you would leverage those. So in the rest of, in the rest of these slides, I'll go through a specific example doing this. So first, of course, we should say that this is not going to be an end-all solution because it's not going to work in all cases, right? It's not always possible to ensure invariance of loss and fairness. So in the paper, we go through these derivations a little bit more and show that under a specific class of covariate shifts, a solution does exist, okay? And that the solution is worst case optimal. So that I'll leave that into the paper if you're interested. And we did that for a specific common algorithmic fairness metrics like demographic parity. All right, so in this case, I also wanted to go through this example because it pertains to a little bit more higher dimensional example than the simple flu one that I previously showed in the previous work, right? So that was a little bit simple graph, a nice exemplar. But in this case, we're now looking at a much more complex graph, and it's for an acute kidney injury prediction task. So for folks who might be familiar, acute kidney injury can happen in a matter of hours, and there's a high risk of patients developing this when they're in hospital because they might be subject to other treatments that could be, difficult for their kidneys, and certain patients might be very at risk for acute kidney injury while they're hospitalized. And so it's an important task to predict on very, small timescales. So we use data from the MIMIC freely available data, which is from a series of ICUs. And we posit a kind of general causal graph on the right-hand side. In the paper, we see how we get this graph. And it includes features such as patient demography, lab tests, comorbidities, etc., described here on the right-hand side. And we're training on an original data set and testing on different shifted versions of the data set. And in this case, what we do so that we can show systematically how this approach works for what degrees of shift, we're going to artificially add measurement error into one of the lab tests. Okay. And using the graph, we identify the invariant distributions to such shifts. Okay, so that's the general idea of the approach. And then how does it look in the results? In the title kind of broadly summarizes, we have stable. So in this case, we can guarantee stable accuracy in our new test environment and low unfairness. So we compared it to some other learning algorithms. And what I'll just broadly do for the sake of time is just highlight that for our method, which is the fair learning with causal DA with the fair learning, the red and the triangle points, you see that the accuracy maintains high as you increase shift on the x-axis. So you have more and more shift in your test environment, distribution shift, but you still maintain a high accuracy. Now, you don't maintain the highest accuracy, which is if you didn't lose any of the information, which we kind of admitted to at the outset. But you can see on the right-hand side, though we didn't retain the highest accuracy, that we did retain stable accuracy, we did have the lowest fairness violations. Again, that demographic parity measure I discussed. As we increase the shift, we still maintain fairness. Yeah, so this kind of repeat of that. And so, yeah, just a summary is that we limit what we can learn to remove any possible areas of instability, and then we can ensure our fairness and good accuracy in the test domain. Now, this I just want to kind of wrap up this section with a little bit of other work that's ongoing, because this could have come earlier, but I wanted to focus on the algorithm before sharing this. So we're actually doing some follow-up work to see where possible shifts can occur in real such healthcare ICU data sets. So in this case, what we did was take data from the EICU, again, publicly available data sets from different ICUs, I think with a specific, I think it's through Philips. And what we did was use the fast causal inference algorithm. So it's kind of a well-known causal inference approach, which starts with basically all your variables in a fully connected graph and then uses conditional independence to prune out edges. And so that's how it determines what the causal relationships are. And so we did this, including different indicators for environment. So on the left-hand side, you can see the different rows. So we looked at if there were differences by hospital, differences by region, number of beds in the hospital, if it's a teaching status or not, and then we looked at the distribution of race variable. And so the columns are different variables that we're looking at. Okay, were there statistically significant shifts in these different variables like age or race or heart rate across these different indicators? So so across hospitals, were there significant shifts in the weight temperature, the temperature distribution, or the BUN distribution. And so you can draw a few conclusions from this graph. First of all, there are significant shifts in all categories of the clinical variables. So just to highlight again that this shifting of the distribution shifts is an important problem. And more so, and this will lead to the next paper, which I'll go through a little bit more briefly, is that there actually was differences in these different variables according to the population distribution as well. And so that's harder to get to the root of. Either the healthcare practitioner, it could be one of two things. Either these population differences result in different lab measurements and different types of variables, or we have different practices for different population groups. And so our paper kind of delves into that in the conclusion, but the main idea is to show where these possible distributions can occur, distribution shifts can occur in real data sets. And there's a question, how does magnitude of shift being evaluated? Yeah, so there's a couple different metrics we use. I'll actually, because I just want to finish up the last part of the talk, but I'll actually refer you to the paper. We looked at some common metrics that people use and did some standard statistical tests to see if there's significant differences. But yeah, I'll loop back to you on that question afterwards. All right, so yeah, so this last finding that you know, we had differences in the population distribution is a little bit good motivation for the last paper. So I'll just pause a little bit to see if there's any other questions. Ali, I'll get back to you on those, what those metrics are for the shifts.
I guess we can ask all the questions at the end.
Okay. Okay, so I know I'm watching the time, so I think the next one I won't be able to go into like as much detail, but I will just give an outline of what we're looking at. So this work is building off this last part. It's looking at basically a new definition of algorithmic fairness based on some of the work in the epidemiology literature as well. And so the main idea here is that capturing fairness, so like we saw with the red hair example, fairness is usually, these algorithmic fairness metrics are usually described in terms of a sensitive variable that is categorical. For example, you can have different gender groups or age maybe groups, or race groups is often used. But specifically for some of these sensitive attributes, there is a lot of work on the epidemiology side discussing how we need to think about these variables beyond looking at attributes of the individual, because there are population level factors, and I'll define those a little bit more for the group, that also affect those individual level parameters. So for only being fair to, for example, maybe different race groups, we're kind of missing out on the broader context that shapes those groups as well. Okay, so I'll go through the definition here because that'll help me define the work, but I'll have to go a little bit quick after that. And so another, besides the algorithmic fairness metrics, which we looked at previously, like demographic parity, there's another in the literature algorithmic fairness approach, which is looking more at causal graphs and the mechanisms in those graphs. So again, this work also leverages causal graphs. And this is called path-specific counterfactual fairness. I put the paper that defines this here on the bottom. And basically this says that a decision, so your outcome, in this case, Y, is fair if it coincides with the one that would have been taken in a counterfactual world in which the sensitive attribute along the unfair path were different. So this definition, again, leverages the causal graph. And this example here is from the paper where they look at actually a little bit, it's a famous case at UC Berkeley where there was some alleged bias by gender in graduate admissions. So basically, let's look at this in terms of the graph. So Y is the outcome, like the admission decision. A is that potentially sensitive attribute, in this case, gender. And what was found is that female applicants were rejected more often than male applicants. But what was interesting is that it was because they were more often applying to departments with lower admission rates. Okay, and so it gives a good example of a type of problem where you might have a fair path and an unfair path to the decision. If the decision was just based on the gender, we would call that unfair because we don't want the decision to be based on the gender. But if it's through the department of where they applied, right? So this black line, the fair path, well, it's named fair because that's acceptable for us in our definition. So it would presuppose that we have, again, the graph of what we're looking at, but also an idea of what we accept as fair and unfair. Okay. And so what I'll do is just outline our approach, and then I can take some more questions because we won't have time to go through the whole thing. So basically what we do, and this is getting a little bit complicated on the slide, so I'll just talk through it. So don't worry about trying to decipher everything here. We basically take the same idea of path-specific causal fairness, but we incorporate the idea that I showed in the previous slide that attributes at the individual level can also have influences at the population level. So for example, you can think about specific health outcomes, and they might be influenced by someone's smoking status, right? If someone's a smoker, that could affect maybe cardiovascular disease status or another outcome. But the fact that someone's a smoker could also be influenced by the types of surroundings that they have. This has been shown in the literature. If there's like many more venues that sell cigarettes, people are going to smoke more. So that would be the population variable, which is this, prevalence of smoking, of cigarette availability in the environment. And so what we do is basically expand that graph like we had in the previous slide to include an exemplar graph to now include population level parameters. And we go through how we show all the arrows in the paper. And then we have an algorithm which allows us to, again, remove the unfair information and replace it with the counterfactual information for the unfair pathways in this multi-level model. Okay, so that's like the broad idea of how we approach this problem. I'm not going to go through the math because it's going to, we're out of time. But for anyone who's interested, please do check out the paper. It was published at the AAAI Ethics and Society Conference last year. And so we go through our approach and we show that we do better than not considering the unfair paths, and also not considering the unfair paths in a population structured system. All right. So I want to thank all of my students who do all the heavy lifting and funding sources. And yes, I left a few minutes for some more questions, so happy to take those.
Thank you very much, Rumi, for your talk. Let me just, Ali, if you want to ask your question in person, you can ask. Yes, we can ask to Ali's question. So his question was about measuring the magnitude of shift and how it is evaluated.
Yeah, there's certain actually measures that people tend to look at for shifts in some of these systems. They look at not only the shifts, they look at like how the intercept shift in the prediction outcome if you're assuming a linear model, as well as the slope. And so we basically take these these calibration metrics and look at the differences across them. So intercept and slope, meaning how well does your model perform on the same group in the test environment versus the training environment, and does that across all of the groups. So that's a basic overview for you. And then we look for statistically significant differences using a chi-squared test between those values for the slope and the intercept.
Rob, if you want to ask a question, please. Rob, Greg, your microphone is open if you want to ask in person. Otherwise, they can ask. Okay, so Rob is asking, once the DAG is determined, how are your predictions next?
Yeah, that just has to, Rob, that's a good question. Just actually speaks to just leveraging the DAG format. In a DAG, the joint distribution of over all the nodes, you can compute it as the product of the conditional distributions of each node given its parents. So you kind of look at those individual probabilities and you can sum those up to get the joint distribution over all the nodes. And you can do that like for any specific outcome that you have in your graph.
So I have a question about your second work. So you mentioned that, like, if I understand it correctly, that you were trying to match the loss for the test and train also at the violation of the fairness. Are you assuming that this is like similar to domain adaptation? Are you assuming that you have some access to the label data, or?
Yeah, that's a good question. Right. So actually in this scenario, we are assuming no labels in the test data at all. But we assume that it should subscribe to the similar causal graph, but we know there's some sources of instability. So those are the kinds of things we assume, but we don't have to know any of the relationships between the covariates and the outcome in the test domain.
So it's very similar to UDA, unsupervised domain adaptation, but the invariant is the causal graph.
Yeah, exactly. Yeah. Yeah, so that's another way that people have started to do that as well. And I think it would be good to kind of compare those two approaches. Yeah.
And have you ever thought about domain generalization in the case that you don't have access to X, your covariates?
Yes.
Under-
Yeah, absolutely.
Yeah.
Yeah, no, I think it's good. I have to think through like what are, you know, on the like the application side, like where that would come about and how it would fit in. But
This would be like
yeah, I mean,
you only deploy, you don't adjust.
yeah, exactly. Yes, that makes sense. Yeah, we haven't looked into this, but I think it's an interesting problem, especially if you have like a fairness constraint as well. Yeah, because you could have shift in the population distribution as well.
Thank you very much. Is there any other question from the audience? It was very exciting talk, and thank you very much. See if there is any other question. I don't see any other question. So thank you very much for accepting our invitation. It was a great talk. We learned. I learned a lot. So
great. It was a good good questions and a good group, and I'm glad I got to share some of this with you. Yeah.
hope to see you soon.
Yep. Thank
Okay.
you.
Thank you.